Good evening, one and all. Let us continue our discussion of the subject discrete mathematics. And today's topic under discussion is mathematical induction. And for today's content delivery, we are using this prescribed textbook by Kenneth H. Rosen, Discrete Mathematics and its Application from McGraw-Hill Publications, 5th edition. So we are using this book to derive today's discussion contents. So topic under discussion is mathematical induction. Let us just look at the example here. So sum of the first n odd natural numbers. So is n square. This is the statement. So let us take 1. The square of 1 is 1. So sum of first n odd natural numbers. So after 1, the next odd number is 3. So 1 plus 3, that is the sum of the first n odd natural numbers. 1 plus 3 is 4, which is 2 square. So the next odd number is 5. The total is 9, so which is 3 square. So 1 plus 3 plus 5 plus 7 is 16, which is 4 square. 1 plus 3 plus 5 plus 7 plus 9 is 25, which is 5 square. So sum of first n odd natural numbers. So every time we are adding, first there is an odd number, then the next odd number we are performing the addition. Next odd number we are taking, performing the addition. Next odd number we are performing the addition. So this relationship is holding as far as this example is concerned. What is that? If n is my number, the sum of the n odd natural numbers is n square. So this is the generic derivation from this. So the relationship between the next number and the previous number, odd number, is this 2n minus 1. So that's why this is for represented like this. Now, if you look at statement number 1, 1 is 1 square. 1 plus 3 is 2 square. 1 plus 3 plus 5 is 3 square. So Sn will be n square. Now, we have to prove this using mathematical induction. Now, for that, what needs to be done is, we first need to prove statement number 1 is true. Then we have to take some k, which is part of n, and prove that statement number k is assumed to be true. If it is assumed to be true, then statement number sk plus 1 is also true. So whenever we want to prove using mathematical induction, these are the steps for proof by mathematical inductions. The proposition is the statements S1, S2, S3, S4 are all true. So proof by induction has, the first step is we have to prove the first statement is true. The second step is we have to take an integer and prove the statement that S of k implies S of k plus 1 is true. Okay. Once we do that, it follows by mathematical induction that every Sn is true. So let us try to elaborate this. Mathematical induction proof has two parts. Okay. One part is called as the basis step. Basis step indicate what? We are trying to prove the first statement is true. Okay. The second step is the inductive step. Okay. What happens in the inductive step? For all positive integers k, if p of k is true, then p of k plus 1 is also true. Now, to reassert what we said, what mathematical induction says, if you want to prove p of n is true, okay, where p of n is a propositional function, using mathematical induction, there will be two steps. The first step will be called as a basis step, wherein p of 1 is true. We verify that p of 1 is true. The second step is inductive step, wherein the conditional statement P of k implies P of k plus 1 is true for all positive integers k. This assumption that P of k is true is called as the inductive hypothesis. Okay. Now, this mathematical induction proof technique, how it can be represented? Okay. P of 1 is true, and for all k, P of k implies P of k1 implies for all n P of n. Okay. No. So, the same statement wherein we said that sum of first n odd natural numbers is n squared. Okay. Here n belongs to n and these numbers are 1, 3, 5, 7, the odd numbers, and this is 2n minus 1 equal to n squared. Okay. Now, what we have to do, we have to first use the basis step. In the basis step, n is equal to 1. Okay. So, if n is equal to 1, n square also is equal to 1. So, 1 is equal to 1 square. So, our basis step is true. We have proved. Now, what is the second step? The second step is the inductive step. In the inductive step, we have to prove that S of k implies S of k plus 1 for any k greater than equal to 1. Okay. So, it means what? We have to prove that 1 plus 3 plus 5 plus 7 plus, here n is replaced by k, see here. So, it will be 2k minus 1. So, instead of n square, k square we are taking. So, any k we are taking. Is it not? So, here 1 plus 3 plus 5 plus 7 plus 2k minus 1 is equal to k square. Then that can be represented as 2k plus 1 minus 1. Okay. So, which again can be represented as 2k minus 1 plus 2k plus 1 minus 1. So, this ultimately comes to k plus 1 whole square. This ultimately comes to k plus 1 whole square. So, hence what we proved this implication S of k implies S of k plus 1. S of k implies S of k plus 1. So, by induction, we can say that 1 plus 3 plus 5 plus 7 plus 2n minus 1 is equal to n square for every n belonging to n. For every n belonging to n. Okay. So, we'll go for the next example. What we have to prove? 5 such that n to the power of 5 minus n. Okay. So, here we'll be taking the first integer as 0. So, in our basis step, which is the first step in mathematical induction, n is equal to 0. So, if n is equal to 0, then it will be 5 such that 0 to the power of 5 minus 0, which comes to 5, 0, which is obviously true. Let k greater than equal to 0. Now we need to prove that 5, k to the power of 5 minus k. Okay. Then k plus 1 to the power of 5 minus k plus 1. This is the implication part. This is the inductive step. This is the inductive step. So here what we will do is, we will be taking some a which belongs to z. Okay. And k to the power of 5 minus k will be equal to 5a. Will be equal to 5a. So k plus 1 to the power of 5 minus k plus 1. When we simplify it, so this 5a will be replacing this k to the power of 5 minus k value. Okay. So ultimately what we are showing is 5 in the bracket a plus k to the power of 4 plus 2k cube plus 2k square plus k. So this shows that this k plus 1 to the power of 5 minus k plus 1 is an integer multiple of 5. Okay. So 5, this k plus 1 to the power of 5 minus k plus 1. We have shown that this implication holds. As this implication holds, By induction, we can say that this relationship holds. Okay. We'll go for the next example. We have to show that 1 plus 2 plus 2 square plus 2 to the power of n is equal to 2n plus 1 minus 1 for all non-negative integers. Let P of n be the proposition. Okay. So initially P of 0 is true because P of 0 means what will happen? It is 2 to the power of 0. 2 to the power of 0 will be 1. And here on the right side it will be 2 to the power of 1 minus 1. So that both become 1. So the basis step is proved. Now we have to go for the inductive step. In the inductive step we have to take P of k. We have to take P of k. Okay. And we have to go for this assumption 2 to the power of k is equal to 2 to the power of k plus 1 minus 1. Now, this is the assumption we are making now, and we are also saying the implication, that is, the implication is true for P of k plus 1. Hence, what we are saying is that 1 plus 2 square plus 2 to the power of k plus 2 to the power of k plus 1 is equal to 2 to the power of k plus 1 minus 1, which is equal to 2 to the power of k plus 2 minus 1. This is the implication step. Okay. Now, using the inductive hypothesis and assumption of P of k, so what we can say is 1 plus 2 square plus 2 to the power of k plus 2 to the power of k plus 1 is equal to 1 plus 2 square plus 2 to the power of k plus 2 to the power of k plus 1. So this part can be replaced with 2 to the power of k plus 1 minus 1, and ultimately this comes to 2 to the power of k plus 2 minus 1. So this implication also is proved. Once it is proved by mathematical induction, we can say that P of n is true for all negative integers n. There is one more example. We have to prove that 1 plus 2 plus 3 plus n is equal to n into n plus 1 by 2. So same thing, first initially basis step. In the basis step, the value of n will be given as 1. So when we replace 1, it will become 1 into 1 plus 1 by 2. So that becomes 1. So basis step is proved. Now we are taking some P of k as true. That is what 1 plus 2 plus k is equal to k into k plus 1 by 2. We have to prove that P of k plus 1 is true. So P of k plus 1 is equal to 1 plus 2 plus k plus 1. Okay. Which, rearranging this, we come to a conclusion that so P of k plus 1 is also true. Using mathematical induction, P of n is true for all n belonging to n. By the way, we use this link for this example, topper.com, and for the next example we use is doubtnut.com. The next example is 1 square plus 2 square plus 3 square plus n square is equal to n into n plus 1, 2n plus 1 by 6. So initially, in the basis step, the value of n is given as 1. So that 1 square becomes this, replacing all n's by 1. So it becomes 1 into 1 plus 1, 2 into 1 plus 1 by 6, that comes to 1. So LHS is equal to RHS. Now the inductive step. What is the inductive step? P of k is true for k. Okay. So it means what? 1 square plus 2 square plus 3 square plus k square is equal to, replace this n by k. Okay. So the implication part will be P of k plus 1. So then we are rearranging this and we are proving this, the left hand side and the right side as equal. So as this implication is proved by mathematical induction, we are proving that this holds true. This relationship holds